Mark hinted at that. Okay, but the fact that the data from the first and second flyby demonstrate pretty convincingly that there's extensive volcanism on the surface shows that interior dynamics was very important. Okay, and so as Mark had said, from the Mariner 10 days, there were ambiguities about these smooth plains units and intercrater plains units, about whether or not they were mostly crater ejecta or whether or not they were volcanic, and some of them still, are likely to be ejecta. So we don't want to rule that out. It's very clear that abundant amounts of them that we have studied so far appear to be volcanic. So it argues that there was a lot of melting on Mercury, and we need to, those of us who do models of how the interior evolved really need to think about those models that produce melting in the crust and that allow that melt to get to the surface.
And just overall, I mean, given what you know from Mariner 10 and the first flyby, with all this, what's the most surprising part of what the second flyby has shown? I guess for any of you.
I would with the observations of how strong the solar wind magnetosphere interaction is. That was just a knock your socks off observation. We weren't expecting it to be that intense at all. We expected it to be fast, not that fast, and not that intense by any stretch.
And that all has implications for what Ron is seeing in the tail, and you heard the connection. I mean, Mercury is a dynamic place, and this time we saw it is even more dynamic than the first time.
Right. I think the big thing for us that was a real surprise was the distribution of calcium and sodium. The fact that they were so different. That's not something that we necessarily would have expected going in, and so seeing that was like a little bit of a wow. We got to really think about what's going on here, and also detecting the magnesium. We weren't sure we were going to see it going in because it had been expected. We thought we had a chance, but it turns out it's there, and this is because of some technical reasons about the way this whole emission takes place. This was actually the worst chance we had to see magnesium, and we saw it pretty easily. So we expect to have some really great magnesium data coming down the line, in addition to the other species that we will continue to detect, and some new ones down the road as well.
Well, when one looks at an early terrestrial planet, one hopes and expects to see evidence for cratering, tectonics, and volcanism, and so we saw those, and I was a little bit surprised by the amounts, but not flabbergasted. I guess the thing that surprised me most was that one hemisphere of Mercury altimetrically, and just along the equator where we've profiled, appears to be about 30% smoother than the other part. And so it's saying that there's some global scale process that at least operates over long length scale. I don't know that it operates all over latitude scale because we haven't sampled that causes one hemisphere of Mercury to be smoother than the other. So that's something that we're pretty excited to follow up on. The profile that was taken from the second flyby hemisphere is about 30% smoother in terms of.
So,
how do you know one from the other?
Yeah, I was going to say, how would you describe that? I mean,
minus 180 to 90 latitude.
Minus 180 to minus 90. Yeah.
Longitude. I mean, is it solarly locked? Is it the sun faces?
No.
It's in a 3. No, so you can't use anything sweeping up ions. So there's some process that act to smooth one hemisphere more than the other hemisphere.
Can we call one east and west so we can relate it to Earth so we can think of it, understand
Flyby
it?
2 was the in-situ observations and the ranging observations were from the western hemisphere.
Flyby 2 would be western hemisphere.
Flyby 2 would be
Flyby
western.
Okay,
one is the eastern.
that puts it in terms we can
So the
sort of
western hemisphere is smoother than the eastern hemisphere. Okay.
Thank you very much.
Okay.
But can I just add that's for a little profile across, right, rather than the whole.
Yeah, just
so
along
it's a little
that
misleading
equator.
to say the hemisphere. It's a profile across.
Right, yeah.
But
the
in
ultimate
a
indicator
real
was
simple-minded
very
world, you could just interpret
linear.
that as older and younger. Because as surfaces sit exposed, they get more impacts on them. So it could have something to do with the relative ages I mean, everything on Mercury is ancient. Don't walk away with it. Something happened yesterday. But maybe, the profile imaged area or sampled areas that were 3 billion years old where it's smooth, and there were 3.8 billion years old where it was ancient, just, off the cuff.
Right.
So that's a simple explanation. There are many other, routes to go down.
Yeah, I'd like to just say that the surface is ancient, but the exosphere, magnetosphere, they're changing on time scales of days, hours, minutes, seconds. And so once you get away from the surface, it's a very dynamic system.
You guys are welcome to have any other follow-ups before I... Seth, you fine? You okay?
I could answer the surprising question.
Oh, yeah.
While everybody was going down the line here, I was trying to think, okay, which one am I going to talk about? But we've talked about smooth planes a lot. Let's talk a little bit about this mysterious dark blue material. We had hints of that from Mariner 10. And the disadvantage of Mariner 10 was that it didn't have these modern, CCD cameras that we've got, that have much higher sensitivity. And it only had this one view of the planet. Now with Messenger, we've seen all the way around the planet. And we were initially interested in these materials from Mariner 10, but we didn't know whether they were small and they were insignificant, or whether they're really important in the big picture of Mercury. And now we see that they're spread over the whole planet, and they appear to be excavated from depth. And it was ambiguous from Mariner 10 whether these were superficial deposits, or were they part of the crust, or what exactly were they. We didn't know. We knew that they were there. We knew that they were possibly important, but now that we see that they're from all over the planet, and they're getting excavated from depth. And if you see two craters nearby, one right here will excavate this dark blue material, and one over here won't. So if Mercury is just this even layer cake type geology, you would expect with blue material here and then the redder material here, that every time you have a crater of X size, it's going to bring that material up. But it doesn't. So that shows that Mercury's subsurface is very complicated. It may be, I don't like to use the word layer, but it may be layered, but the layers are discontinuous, or they have a lot of topography, or there are no layers at all. There's just intrusions that came up and deposited this material at depth. So it's telling us the bottom line from this is that the crust is very heterogeneous and it's very complicated. And we really want to get into orbit so we can get some geochemical measurements of this material, so I can stop saying blue material and I can stop saying versus red material, right? And tell you that it's a, kind of strange basalt, or it's a type of, other rock that we know and love. But right now, we're just, stuck in this color jargon until we can get into orbit.
And once again, just to blue, we keep calling it blue material, but in visible light, it's it would be darker.
Well, it is
darker gray.
To your eye. Let's say if you were in orbit over Mercury and you had a very sensitive eye, you would see it as being a little bit, darker in reflectance, and it would have a very slight blue tinge, or it'd be less red. And actually, I think a good example of this, when you look up at the moon, what colors do you see? It's black and white, right? But, however, when the Apollo astronauts were in orbit around the moon, they saw subtle shades of bluish and orangish tints on the surface because they were closer, and the sun was right overhead, which enhances subtle color differences. So I don't know exactly what you would see. It also depends probably if you were an 18-year-old or a 50-year-old, right? But I think you would see them as something different. But they wouldn't be that garish blue that I showed you in that process. Because remember, that's a combination of visible and infrared.
And your best, granted you have to wait to get more data, but if you had to guess now on what kind of material?
Okay, well, there's a couple of theories that we're working on. One is that the blue material may be affected by the presence of opaque minerals. And a good example of that is ilmenite, which is not a totally crazy idea. We see ilmenite on the moon in much higher concentrations than you see in most similar rocks on the Earth. And this is a mineral that's rich in iron and titanium. And it's probably, don't think in terms of, well, it's a deposit of ilmenite. Okay? It's a material that maybe has a few percent or 10% ilmenite in it. But we don't know that for sure. But it's very interesting that if it is ilmenite, it's telling us something fundamental about the bulk composition of Mercury and the evolution of the mantle to the crust.